Good evening. I'm kind of soft-spoken, so let me know if you can't hear me, and I'll try to talk louder. But my name is Tim Heberink. I work in the corporate research labs at 3M, and it's my pleasure to tell you about the exciting renewable energy technologies that are being developed there. So over half of 3M's products are comprised of films, tapes, and adhesives. I also have to tell you there's a lot of films that 3M has been selling for 50 years into the renewable energy, starting off with window films for energy efficiency, and Fresnel lenses. 3M started selling Fresnel lenses for concentrating solar light about 20 years ago. So 3M's really been in the renewable energy business for 50 years. It's just in the last few years that there's been a strong emphasis, a focus put onto it. So if we go down the line here, there's mirror films and Fresnel lenses for concentrated photovoltaics. We're making the world's most reflective mirror films for concentrated solar power. That's for heating water and generating electricity from steam. Barrier films, which are weather resistant and keep moisture out for making flexible photovoltaics. And then lots of tapes and adhesives that just make the package around a photovoltaic cell more durable and more weatherable. So for the last few years I've been leading a durable films team, and the goals of that team are to make these polymeric films more UV stable, more dirt resistant or easy to clean, and more abrasion resistant. These are requirements that our customers have. They offer warranties for 25 years, so 3M's products have to be durable. We believe that it's important to make prototypes, and I brought some to show you. I'll tell you a little bit more about them later, because you'll learn a lot by doing. We also have some really good physicists that do optical modeling and help us understand how to design these things and why they don't work when they don't work. Really believe that if a picture is worth 1,000 words, a prototype is worth 1,000 pictures, and that's a lot of words. So the business strategy for 3M is to lower the cost of generating electricity from renewable energy. So basically targeting this dollars per kilowatt hour, and we're doing that in two ways. We make tapes, films, and adhesives that reduce the fabrication costs. They allow people to make modules and other components with lower costs. We also have films that increase the power output of a module or a solar thermal panel. So you can get at this by either increasing the denominator or decreasing the numerator. Ultimate goal. Here's a sampling showing where these products go. So for the junction backs on the back of a photovoltaic module, we make this solar acrylic foam tape. It's a soft, compliable tape. It's especially good where you have two materials that have different coefficients of thermal expansion, say glass and aluminum, and one expands faster than the other when it heats up. We also have adhesive sealants that provide waterproof around the perimeter of that junction box. Scotch Shield 17, I was telling you, was the most successful product in the last couple of years. That's a very durable back sheet that goes on the back side of the module. Seals the water out, very UV stable, and has good electrical insulation properties. We also have specialty tapes for the perimeter of the photovoltaic module, cell positioning tapes, and labels. In addition to that, we have these charge collection tapes which conduct electricity, so you can just stick them on a module and use them as the electrical bus bar to collect electricity. So this previous one was a crystalline silicon photovoltaic cell, which is what most people are familiar with. It's a rigid cell. This one is a thin film photovoltaics, which are becoming more popular. And so we have a lot of products that go into both the crystalline silicon rigid and the thin film. So again, we have cosmetic specialty tapes, acrylic foam tapes, labels, and these things all help in basically providing the weatherable sandwich that goes around the electronics and keeps the electronics intact and provides them integrity for 25 years. One of 3M's core businesses is fluorinated fluoropolymers, which are the most UV stable polymers known to man, and therefore it was pretty straightforward in using them in our first products. But one problem with these fluorinated films or materials is they don't adhere to things very well. So there's a lot of unique proprietary technologies that 3M has figured out to get these fluorinated films to adhere to other things like the backside of a photovoltaic module. Mostly what I've been working on is solar light management technologies, so technologies which allow you to capture more sunlight and get more sunlight into a photovoltaic cell or solar thermal panel. We just recently launched, this is actually a resurrected product. This product was launched in the early 90s when there was some interest in solar thermal back then. And then 3M discontinued the product for about 10 years and just relaunched it a couple of years ago. And it's new and improved now. It's more weatherable than it was back then. And it's a silver-coated PMA for concentrated solar power and solar thermal. Multilayer optical mirror films, which I'll go into a lot more detail about because this is an area that I focused on for the last 15 years. It's a very unique technology for 3M. But films are just films until you make them into something rigid. So there's 3M has been partnering with other companies to turn these into rigid components that will withstand 70-mile-an-hour winds and the flexing of, that occurs out in a desert storm. We also have structured surface films and coatings that are basically anti-reflection. If you look at a piece of glass, a window, there's 5% of the sun's light gets reflected off that front surface. These coatings and films capture that additional 5% of light. And then all of these products, the mirror films, the photovoltaic modules, the solar panels, and even window films, they all attract dirt. They all get dirty. So 3M has some unique anti-soiling coatings that not only make the films and the windows easier to clean, but they actually repel dirt. So this is a technology that I've spent a lot of time on in the last 15 years. It's a very sophisticated technology where we make these quarter-wave constructive interference mirror films. They're comprised of hundreds of layers of alternating materials, where one material is a high refractive index polymer and the other one's a low refractive index polymer. And we bring them together in a manifold and make a film out of them. And if you make those layers a quarter wavelength of the light that you want to reflect, you can get 99% reflection. And basically, every layer pair here reflects about 5 nanometers of light. And if we're talking quarter wave of blue light, which is 400 nanometers, and the layers are only 100 nanometers thick. If you're talking a quarter wave of red light, they're 150 nanometers thick. And what's really unique about them is you can tune the reflection band by just varying the thickness of these layers. And a lot of people look at this and say, well, how many coating passes does it take to make that? And these are not coated, they're co-extruded. You take polymers, you co-extrude them together, and you make them into a film and you stretch the film. And so what we brag about here is we are able to control the layers of these films by the nanometer, but we make them by the mile. We literally make jumbos of film that are a mile long and several meters wide. And what's kind of fun about this is this takes off technology that's all around you in nature. All around you in nature, butterflies, beetles, they use differing refractive indices of materials to reflect light and give them color. The feathers on birds, so it's out there already, and 3M has taken advantage of this unique technology found in nature and figured out how to mass produce it, basically. The basic equation, again, is you have 2 different polymers, and the reflected wavelength of light is 1/2 the thickness of the 2-layer pairs added together. One polymer has a high refractive index, the other polymer has a low refractive index. And depending on which polymers you choose and their refractive indices, you can make the bandwidth, the reflection band, very wide or very narrow with high reflection. Prior to 3M coming up with this technology, people were making these mirrors, interference mirrors, on glass by coating the glass with a real low refractive index silica and alternating it with layers of a real high refractive index zirconia. You can get good mirrors that way, but it's an expensive batch process. You got to go layer by layer. And then there was another company actually before 3M too that made some of these films with polycarbonate and PMMA, but Where 3M really took advantage is we started using birefringent polymers. And birefringent polymers, you're able to get a polymer, a flexible film with real high refractive index, and therefore get a very high optical power. To get a broad reflection band, you need a lot of layers. And this basically shows you have a gradient of layers from the top of the film to the bottom of the film. And so if we have 250 layers, at one side of the film, the layers are 100 nanometers thick. They're reflecting 400 nanometer light. And this shows the power of reflectivity with the difference in refractive index. So the difference between the refractive index of material 1 and the refractive index of material 2 allows you to get materials that are incredibly reflective. We've made films that are 99% reflective. They're the most reflective mirrors in the world. Your typical silver-coated glass mirror in your bathroom is 94% reflective, and aluminum mirror is typically about 90% reflective. Another interesting characteristic of these films is the reflection band shifts with angles. So at normal angles, you'll get a reflection band that is, say, in this case, this is an infrared mirror for putting on windows. So it'll reflect 1100 to 1800 nanometers. As you go off angle, that reflection band shifts to the left. And for a window film where you don't want to reflect any visible light, you want to put that reflection band far enough out in the infrared that when it shifts to the left, it stays in the infrared, and the left band edge here stays above the visible light region, which is 400 to 700 nanometers. This is another cartoon showing a cross-section of the film where we have alternating layers, high refractive index, low refractive index, high refractive, low refractive. And what's unique about birefringent polymers is when you stretch them in this direction, the refractive index goes up in that direction, but it goes down in the thickness direction. So it allows us to make unique mirrors where in the thickness direction, the Z refractive index is matched between these materials. And that allows you to break an old law of physics called Brewster's Law, where the reflectivity stays very high as you go off angle. Here's another cartoon showing how we make these films. We have these film lines with extruders, which basically melt polymer pellets and bringing them together in a manifold like a car engine, except instead of eight manifolds, we have 100 to 300 manifolds. And they alternate the layers, and it comes out of a die like this and is quenched on a casting wheel, and then the film is stretched. And by stretching it, you make the layers thinner, get them down to nanometers thick, and you make them birefringent, which gives them a very high optical power. This cartoon showing the manifold where two polymers go into two different manifolds side by side, and then out of each manifold comes hundreds of layers that come together alternating. And then we also have a machine here for orienting the film. Sometimes there's two steps. We stretch the film in the machine direction to give it birefringence that way, and then we stretch it in the transverse direction to give it orientation that way. Again, that gives the film thinness, it increases the modulus, gives it strength, and greatly increases the refractive index to give it the optical power we need for reflecting light. So there's a lot of unique things about all polymeric mirrors, mirrors that don't have any metals in them. One is they can be thermoformed, and so you can take a piece of film, heat it up, and stretch it over a form to make unique form factors like this. And these are not products that 3M intends to sell, but we just make these so we can show people the possibilities. The possibility that you can make a photovoltaic module that's all polymer. And the real value here is that the polymeric mirror film is about 1/10 the cost of the photovoltaic cell. So you have photovoltaic cells here that are roughly $200 a square meter, and this mirror film is about $20 a square meter, roughly. And so you can make a module with half as many cells, and by replacing half the cells with mirror films, and drop the cost by 30 to 50%, depending on how efficiently you do it.
Why aren't they making them to sell?
Well,
You won't make enough money if they're cheap.
the ultimate goal is to get the cost down, so the cost of electricity is equal to that with the grid, right? So if you can get the cost of electricity From solar energy down closer to what it costs to make it with coal or nuclear, more people will use it. So it'll become mass adopted. So that is the ultimate goal, is to get it as cheap as possible. So these mirror films are 98% reflective, the most reflective in the world. They're also tunable. So like a photovoltaic cell really only uses a portion of the sun's light. It uses the visible light and a little bit of the infrared light. The rest of the infrared light, all that does is goes into heating up the cell. The hotter the cell gets, the less efficient it is. Most electronics, the hotter they are, the less efficient they are. So these mirror films, we can tune them so they only reflect the wavelengths of light that the photovoltaic cell uses. But we're also able to make UV mirrors, which are unique in that they can be used to protect anything that degrades under UV light. Yeah.
Roughly how many layers is this?
How many layers? About 600. Yeah. Yeah. So UV mirrors are good for protecting other things, including other polymer films. Some of these polymer films are not UV stable, so we put a UV mirror on top of them and make them UV stable, or they can be put on windows to protect anything inside your building that will degrade from UV light. Visible mirrors are good for concentrating sunlight, but also just good for transporting light in a building for daylighting. So you may have heard of a product called Solitube. It uses 3M mirror films to bring light from the roof into a building. And recently, we've come up with new designs to bring light in from the side of a building. Well, you'll use these concentrators to concentrate the sun up into a duct, and then the duct brings the light in from the side of a building. You get really good energy efficiency by using daylighting. The near IR mirrors are used mostly until recently for rejecting infrared light for windows. So automobile windshields and the sides of buildings, you can greatly reduce your air conditioning costs by using these near IR mirrors. And then we can laminate all these together to create a broadband mirror, which is most useful for the solar thermal applications where you want to heat something up. And then reflective polarizers. This has been one of the most successful products that 3M has made because of the mass popularity of liquid crystal displays. So everybody here probably has a cell phone, maybe a smartphone, laptop, liquid crystal display TV. Almost all of those contain a 3M film. That 3M film makes them more efficient, and it does so by only reflecting one polarization of light, and then allows the other polarization to pass through. Reflects this one, allows this one to pass through. And so that's more of an energy efficiency, and I'll tell you a little bit about that here. So in a laptop, you can increase the energy efficiency of your laptop by 60% with these reflective polarizers. You can use that to either make the laptop screen brighter, or you can use a smaller battery or less battery, or increase your battery life so your battery goes longer. This works because in a liquid crystal display there is an absorbing polarizer. And there's an absorbing polarizer on either side of the liquid crystals. These are the pixels that make up your display. On either side of that, there's an absorbing polarizer that's crossed. If you don't use our film, half the light that the bulb generates is absorbed by that first absorbing polarizer. But if you use our film, you put our film, in this case called DBEF, in there, it recycles that light. The polarization of light that would be absorbed by this film is reflected and goes back until its polarization basically turns until it can pass through the absorbing polarizer. And by doing so, you can make a large TV with 12 bulbs instead of 16 bulbs. And it then generates, consumes 145 watts instead of 80 watts and runs cooler, so it doesn't heat up your house as much and you don't need as much air conditioning. So this is one of our most successful products. Again, more energy efficiency than renewable energy, but it's important, very important for your energy efficiency is the first thing you need to do before you do renewable energy, by the way. Yep.
Tim, is that stuff that is used like on the dash of automobiles and stuff?
Yeah.
Because I was in a new Chevy Volt piece that they were talking about that.
Yeah, a lot of the newer automobiles have liquid crystal displays. If they have a liquid crystal display, it's probably used. Some of them use LEDs, and then we actually have a newer product that works for LEDs though too. That conserves the light out of an LED. So here's a cartoon of the solar spectrum. This is the light that the sun generates relative to the wavelength. And so what we see is visible light here. It's just a small portion of the whole solar spectrum, 400 to 700 nanometers. That's the light that you see. There is all this light beyond 700 nanometers that you don't see. A portion of that is used by a photovoltaic cell. So this portion from 400 to 1200 nanometers is used by a photovoltaic cell. Visible light and a little bit of infrared light is used by a photovoltaic cell. This infrared light out here is not used by a photovoltaic cell, so all that does is heat up the cell and cause it to be less efficient. So this chart shows the power output of a photovoltaic cell as its temperature goes up. As the cell heats up, its power output goes down, the voltage goes down. So this is where we really take advantage of 3M films, because our mirror films are wavelength selective. Rather than a silver-coated mirror film or aluminum reflects all these wavelengths of light, we can design it to just reflect the wavelengths of light that are desired to reflect. So this is a simple design that I'm passing around. It's called a low-X concentrator because it's only concentrating the sun by two times. There's a lot more complicated ones where you can concentrate the sun by 3 times, 10 times, 100 times, 1,000 times. But this is simple because it's easy to describe here. The sun's light hits the mirror on these prototypes. The light that is useful to the photovoltaic cell gets reflected onto it. The light that's not useful passes through it and gets reflected away. So the photovoltaic cell does not heat up. We're branding this as cool mirror film, not just because it's cool, but because the cell operates at a cooler temperature and therefore more efficiently. This is my house out in Scandy, Minnesota, where this concept was first tested about 5 years ago, and just put together bought some modules, put the mirror on either side, and proved that we could get 70% more power out of each of these photovoltaic modules with this film that costs 1/10 what a photovoltaic module costs. And we're delighted to have a brand new customer in Bloomington, Minnesota, 10K Solar. They're our real first successful commercialization of this product. And they have a unique design that is a non-tracking design. And it uses our mirror film right here. The mirror film is positioned here, shown here in a picture in their parking lot in Bloomington. And basically it reflects the sunlight off the front of the cell onto the cell, and you get 50 to 60% more power out of each module. And they've got several smart things about their design. In Minnesota and northern latitudes, if you have rows of photovoltaic cells like this, they have to be spaced out. Otherwise, the row in the back gets shaded by the row in the front in the wintertime because the sun's lower in the wintertime. Well, you got this empty space in here. Why not use that empty space? And that is the really smart thing that 10K Solar did. They filled that empty space with our mirror film. And now in the summertime, you get 50 to 60% more power out of these their module for a film that's a fraction of the cost of the module. And here's another demonstration that we have going at the Science Museum. It's similar to this one I'm passing around. Unfortunately, we've had a lot of struggles with the tracker on this thing, so the tracker has not been working, and we're still troubleshooting that. But when it's lined up with the sun, it produces more sun per cell, and we will get that working, so it's a good demonstration. And here's another demonstration we have that works well on commercial flat rooftops. This is a similar demonstration of these designs that we put on the roof of the University of Nevada in Las Vegas. And it uses a unique tracker that's simple. It's like a lazy Susan that you put on your dining room table, right? It just turns in one direction. It's a single axis tracker. It's inexpensive, lightweight, and it's very effective. It's low cost because it's just a single axis tracker. And you don't have a pole. It's pretty difficult to put a pole on the roof of your building. This sits on a flat roof and handles the wind loads well. And we find that when we put our mirrors on here, we get twice as much power out of every cell with this design when it's tracking the sun. So basically, if you don't track the sun, you get about 50% more power, roughly, out of every cell with our films. If you track the sun, you can get 100% more power. And with the more sophisticated parabolic designs, you can get a lot more than 100% more power out of it. but then you have to add, then even our cool mirror film is not enough. You have to put some sophisticated heat management designs on the back of the cells to take away the heat. One thing we found though is polymers attract dirt faster than metals do. You probably knew that already. So these polymeric mirror films need to be cleaned more often, but you know, the need is the mother of invention, and so 3M has come up with some new anti-soiling coatings that we can put on these mirror films so that they don't require to be cleaned so often. And here's an example. You can also put these coatings directly on a photovoltaic module. So this module is half coated and then covered with dirt, shaken and tipped upside down. And you can see where the dirt just fell off this coating here. And this is more important in the desert, say, than in Minnesota, where it rains frequently enough here that your modules get washed off naturally. But in the desert, the dirt just builds up, and they'll actually hire people to go out with trucks and hose down the modules where they have large solar fields in the desert. And as you might imagine, there's 100 different kinds of dirt. The composition of dirt changes all over the world, and depending on what the composition of the dirt is, you need a different coating. In some parts of the world, you need a hydrophilic coating, which wets out water, and other parts of the world, you need a hydrophobic coating. So 3M has a portfolio of coatings that you can provide, put on your module, put on your windows, depending on where you live in the world and what kind of dirt you have. Here's another unique core technology 3M has. It is micro-replication. 3M uses micro-replication for a lot of things, including brightness enhancement films and displays again. This particular one is a fun one. It was developed back in 1990. It's called riblet. It's actually in the dictionary. If you look riblet up in the dictionary, it'll say 3M drag reduction film. And this was used in 1993 to help the American sailboat win and the year later they outlawed. They said nobody can use this 3M film anymore. It's an unfair advantage. So, but last year they said, well, as long as 3M offers it to all the teams, you can use it again. And this BMW team used the 3M film on their catamaran here, and they won the race. So both times the 3M film's been used, the sailboat that used it won the race. Kind of a fun demonstration of the technology. But basically what it does is it reduces drag. And it was originally developed for airplanes. But we found a new use for it. When you put this film on the front side of a photovoltaic module, you get 5 to 10% more power out of the photovoltaic module. And that's because at normal angles, when light hits the glass on the front side of a photovoltaic module, 5% of that light's reflected. But as you go off angle, even more of that light's reflected. And these surface structures capture that light and bring it down into the photovoltaic cell. This shows how a 30-degree prism, this is the percent transmission, and this is the incident angle. So 0 would be light coming in at a normal angle, and 90 would be light coming in at a glancing angle. And it's optical modeling that shows if you have, say, just a flat polymeric surface, you get 96% transmission at normal angles. But above 45 degrees, the transmission just drops incredibly. But you put these surface structures on there, and you can get 99.5, theoretically 100% of the light into the module. And even more importantly, off angle, at higher and higher angles, you capture more of that light. And this shows how the sharper the tip, smaller the apex angle, the more light you can capture off angle. And this is another way of illustrating it. At normal angles, you get 95% of the light through the glass, but with our film, you get 99.5% of the light through the glass. And at high angles, you get way more, 50% more light through the glass. And this shows a module with the structured surface film on the front of it. And you can see this one here has no surface structured film. You can see significant reflection of the sun's light. That's light that's lost. That's light that doesn't generate power. And here, 5% more light gets into the module, so you get 5%. We've measured 6 to 10% more light initially with certain designs under just the right conditions. So we had a fun project with the University of Minnesota last year where every year they build a solar vehicle that they compete with a race. And we put this structured surface film on modules. We provided them with a structured surface film. They put it on the modules and built their car with it. And previously they had done it with a fluoropolymer sheet. And our surface structured coating gave them 4% less surface reflection and therefore 4% more power out of their car engine. And these are some fun pictures showing the students and the car they built. And every one of these photovoltaic cells here has a 3M anti-reflection surface structured coating on it. And the fun thing is they took second place out of 30 cars in their cross-country race. I guess every other year they have a cross-country race, which is roughly a 1,000-mile race, and then in between years they do a speed race where they go around a track as fast as they can. One of 3M's advantages is we have a very extensive weathering resource center where we do predictive modeling of how long a polymer or any material will last outdoors. This is down at Cottage Grove where I'm sure you know most of the traffic signs in Minnesota are made with 3M materials, so we test all these materials outside. And then indoors we have these accelerated weathering chambers where we expose materials to more light, 10 times the light they would see outside, and heat and humidity. And by cycling materials through all these conditions, you can create models that allows you to predict how long they'll last outside. And this is a huge advantage for 3M developing polymeric films, tapes, and adhesives that are intended to last outside a long time. And down here are lots of examples of 3M products that have been used outdoors for years. Traffic safety, commercial graphics, automotive emblems. All these things are used outside and are expected to have long lifetimes. So there's a big advantage that 3M has this internal capability. And with these, you can predict how long products will last. So this is just an example product. You find out by doing this that some polymers are more susceptible to humidity, so they won't last as long in Florida as they will in Arizona, and of course in Minnesota they last much longer because there's less sunlight and heat here. But with this, it helps 3M provide warranties on products, so we can figure out how long a warranty we should have on a certain product. I told you a little bit about the solar thermal applications. So 3M recently launched a product called SMF 1100. It's a silver-coated PMMA. It's out in Colorado right now in a large trough installation like this, heating up water that's used, and it's being demonstrated in multiple places. But this has a huge potential. People keep talking every year that there's going to be more and more of these large solar farms put in the desert. And basically the mirrors concentrate the sunlight on a hot oil. The hot oil goes to a reservoir. From that reservoir, it generates heat, exchanges heat with water, generates steam. The steam runs a traditional steam turbine. Or you can put these on your house or your business and heat water for your process or your building heat. You probably heard a lot about this one in the news recently. So 3M has got a large award from the Department of Energy for developing a better film that will enable flexible photovoltaics, and in particular SIGs photovoltaics, which are copper, indium, gallium selenide. They're different than silicon. You can flex them, and the goal is to turn these into roofing membranes or shingles. So they not only generate electricity, but they are your roof. They're what keeps the weather out of your house. So the advantage of this is you can get away from glass. Glass is heavy, it breaks, and the balance of system costs is much lower because you don't need all that racking to hold the modules. You can ship this stuff a lot less expensively because you can pack it in on a pallet, get a lot more watts on a pallet. And the real holy grail is if we can make this roll to roll. So you unroll a roll of film, you coat your photovoltaic module on it, and you sandwich it with another roll of film. And that's what 3M does best. We make products from rolls of films, and when you can start making these things at hundreds of feet a minute, you can make them very inexpensively.
Are you looking at incorporating that into like a roof membrane?
Yes, exactly, yep. So could be our first real interested customers are people like John's Mansville that make the rubber roofing membranes on flat roofs, but we also have demonstrations where it's similar to the unisolar module where you can put it on a steel corrugated roof in between the ribs on the steel corrugation. So the unique technology that 3M has is a multi-layer coating process that basically is real thin layers of glass. And so they'll coat glass and another layer and glass and another layer, and that makes a virtually moisture vapor impermeable membrane. And SIG cells are very sensitive to moisture. If they get any moisture in them, they corrode and degrade quickly, much faster than a silicon cell. So SIG cells really require these ultra barrier films to enable them to last 25 years. And that's what got the DOE excited, and they gave 3M quite a bit of money to speed up the development of this product. So we can help bring the dollar per watt cost of generating electricity with solar down. So this is another recently developed coating that just got offered for sale, was just commercialized. And it's another coating that you can put on glass. It's more of a, not a film, but a coating. It increases the transmission by 3%. It's very durable. It gets baked on the glass, and we're offering this to module makers now. It increases the transmission through a piece of glass from 92% to 95%. And just a little commercial for 3M. The real power of 3M is that we have at least 45 core technologies. So 3M reinvented the periodic table of elements here with our different core technologies. And we go to customers, they tell us their problems, and the reason we're so good at solving their problems is we can combine these technologies like no other company can and come up with really unique solutions. And that's a big part of why 3M is successful, is we have a real breadth of technologies besides the depth. You know, we have experts in each one of these technologies. And a little bit about me. I've been generating electricity at my home. 95% of my electricity has come from the sun or the wind for the last 10 years. I really like this picture because on a day like today when it's cloudy, the wind turbine is cranking. The solar cells are only putting out 20% of what they normally would. But these two technologies are very complementary. When the sun's not out, the wind is producing electricity. They're really a good marriage of technologies. And we have fun. I live in Scandia, Minnesota, so we had fun with Sandia National Labs, because we fondly call my house the Scandia Regional Lab. And I do a lot of testing of coatings and mirror films right on my property. Okay. Well, the first week in October is a bad weekend for me. I'm always out of town that weekend. Otherwise, I would love to do it. Yeah, but maybe some year I'll be in town. I'm happy to give anybody a tour other than the first weekend of October. So